Now we are going to define the redox reaction in terms of oxidation number. So before we do that, you should know actually that what is the oxidation number. Oxidation number is the residual charge, it is actually the residual charge which an atom appears to have when all other atoms are removed from it. Or you can say it is a charge suppose I have like this, see, if I have a molecule like KMnO4, if I need to find the residual charge on this manganese. So actually this is a charge which it will possess when K and oxygen is removed from it. So this is actually called as oxidation number. Now in order to find the oxidation number, we have certain set of rules. Just look at the board. The first rule is oxidation number of element in uncombined state is always taken as 0. For example, if we talk oxidation number for H2, if we talk it for sodium, we take it for zinc, then when they are not in a combined form, then at that time you will take the oxidation number as 0. So any substance which is occurring in its elemental form or in a form in which it exists in nature, you are going to take its oxidation number as 0. Second is, for ions, oxidation number is equal to the charge on the ion. For example, if you get to see this kind of thing, Na positive, then its oxidation number is definitely going to be +1. And if you see you can see a ion like this, suppose Cl negative, then obviously its oxidation number is going to be -1. So that means oxidation number is always equal to the charge on an ion. For cations also it is equal to this much positive, for anions also it is equal to that much negative which is present on that. Third, if for an ionic compounds, that is the compounds which are formed between metals and non-metals, one is going to possess the positive oxidation state and the next one is going to possess the negative. Who is going to possess the positive oxidation state? Obviously the metals, and negative non-metals. And if we talk about the covalent compounds, which is formed by the combination of non-metal and non-metal. So there also we need one atom with a positive oxidation state, another with a negative. Now the question is that, like, out of those two non-metals, which will have a positive oxidation number and which will have a negative. So at that time what we see, we focus on the electronegativity. The non-metal which is more electronegative, its oxidation number is taken in the terms of negative, and the one which is less electronegative is taken as positive. So for more electronegative it is negative, and for less electronegative it is obviously going to be positive. And if we talk of hydrogen, so the oxidation number for the hydrogen depends that whether it is bounded to a metal or to a non-metal. If it is bounded to a metal, its oxidation number is obviously going to be -1. But if it is bounded with non-metals, then we are going to take +1. And likewise for oxygen, generally oxygen possesses the oxidation number as -2, but exception lies here in O2F2 and OF2. OF2 you are going to take it +2 and O2F2 you are going to take as +1, right. And now if when you need to find, if I need to find the oxidation number for Mn, so obviously I will be adding all those things. I will take an algebraic sum of all these atoms which are present, and I am going to equate it to certain value. And for neutral molecules we are going to equate it with 0. As you can see, this is a neutral molecule, it does not carry any kind of charge. So we are going to equate the algebraic sum with 0. But if there is charge like this, in this Mn4 negative we have a charge. So we are going to equate the algebraic sum with the -1, that means with the charge which is present on the molecule. Let us take few examples now. See, if I need to find the oxidation number for manganese in potassium permanganate, how I am going to do that? First thing is that just separate the atoms, K, Mn and O4, right. We need to find the oxidation number for Mn. So let us assume as X, and try to write the oxidation number for the other ones, +1, and we know it is -2. Now as you can see that here we have only one atom, so that means you are going to take only +1. Between two atoms we put sign plus. X, because there are no number, if there was 2 we will be writing 2x, if there will be 3, 3x, but here we have only 1, so that means only x I am writing. Again plus, but we have 4 atoms and one oxygen atom has oxidation number equal to -2. So it becomes -8. And because we need to equate the algebraic sum, because it is a neutral molecule now, we are equating it with 0. So just solve it. We get 1 plus x minus 8 is equal to 0, or we have x minus 7 is equal to 0, or we can write x is plus 7. So that means oxidation state for manganese is plus 7. Let us take another example. Mn2O7. Again, I need to separate them. Mn2O7, we need to find for it, and we know that for oxygen it is -2. So what we have? 2x, because 2 into x. 2 different atoms, we put plus sign, -14, neutral molecule, that means we need to equate it with 0. So it becomes 2x is equal to 14, x is equal to again 7. So that means in this case also the answer for manganese oxidation state is again plus 7. Let's take for this. Again separate them. So we need to find for it x plus -8, and we need to equate it with -1 because it carries a minus charge on the molecule. So it becomes x minus 8 minus 1, x is equal to -1 plus 8, and we get again plus 7. So it is a coincidence that in 3 of the cases we are getting oxidation state for manganese as plus 7. It's not like that. Don't ever think like that for a same atom you're going to get the same oxidation number. This is a coincidence that in 3 of the cases it is getting a plus 7 number. Otherwise the oxidation number can be anything. And do not relate the oxidation number to the valency. Keep in mind, it is just valency is the combining capacity, and oxidation number is the residual charge actually which is left on an atom when all other atoms are actually removed from it. Right, so this is the oxidation number. So now we are going to define the redox reaction in terms of oxidation number. So just look at the board.